Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Physical Vapor Deposition from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, the fundamental physics of the physical vapor deposition process will be discussed. Second, detailed study of various types of PVD methods and the difference in their growth processes. Thermal evaporation, E-beam evaporation, pulse laser deposition, sputtering techniques will be discussed. Lastly, we will also study the advantages and disadvantages of all the PVD methods. So students, let us start with a basic introduction about the module. A thin film is defined as a low-dimensional material created by considering one by one atomic, molecular, ionic species of a matter on a substrate. An enormous variety of thin film materials, their deposition, fabrication techniques, spectroscopic and optical characterization increases the utility in the production of devices. The possible techniques used for thin film deposition are broadly classified into physical vapor deposition process and second is chemical deposition process. Physical method covers the deposition techniques which depends on the evaporation or the ejection of the material from the source, that is evaporation or sputtering, whereas chemical methods depends on physical properties. Structure property relationships are the key features of such devices and basis of thin film technologies. Underlying the performance and economics of thin film components are the manufacturing techniques on a specific chemical reaction. So, thus chemical reactions may depend on the chemical formation of the film from the medium, and typical methods involved are electroplating, chemical reduction plating, spin coating, dip coating of a chemical solution, chemical vapor deposition, etc. Physical vapor deposition (PVD) is basically a collective set of vaporization processes that are used to deposit thin layers atomic level of a material, typically ranging from few nanometers to several micrometers. These processes are eco-friendly, vacuum deposition techniques and consist of three fundamental steps. So these are material vaporization from a solid source assisted by high temperature or gas phase plasma, transfer of these vapors to the surface of the substrate in a vacuum or partial vacuum. Next is the condensation of the vapor onto the substrate to form thin films. Now, these are the three processes. So, the common examples of PVD processes are pulse laser deposition, sputtering, thermal evaporation, E-beam evaporation, etc. All the methods, though differ from each other in the growth and deposition methods, they yet follow the above mentioned three fundamental steps. Thermal evaporation. So, thermal evaporation is one of the simplest physical vapor deposition process. In thermal evaporation, an electric resistance heater is used to melt the material in a vacuum chamber till the atoms at the surface of the material gains sufficient energy and leave the surface as shown in this figure. So at this point they traverse throughout the chamber at thermal energy less than 1 electron volt and will get deposited on a substrate which is situated above the evaporating target material at an average distance of 200 mm to 1 mm. High vacuum is required for thermal evaporation basically for two main reasons. First, to allow the vapor to reach the substrate without reacting with or getting scattered against other gaseous phase atoms in the chamber. Next one is to reduce the consolidation of residual gas impurities in the vacuum chamber. So students, in this process, the chamber pressure must be kept below the level, that is 5 into 10 to the power minus 5 millibar, such that the mean free path, that is the average traveling distance for an atom or a molecule in the vacuum chamber before it collides with any other particle, disturbing its direction to some extent, is longer than the distance between the substrate and the evaporation source. Tungsten or molybdenum filament is utilized to heat the source material for evaporation are shown in this figure. Now let us discuss the advantages and disadvantages of thermal evaporation. First, let us discuss the advantages. It is simple and cheap, less substrate surface damage, excellent purity of films. The disadvantages is that there are considerable wastage of source material during the process. Next is confined to low melting point metals. Evaporation of dielectric materials is not at all possible. The amount of material deposited is also constrained by the filament. We get the poor density and adhesion of the film. Step coverage is harder to improve. Crystal monitor. Now, in order to monitor the thickness of the deposited film and also to control the rate of evaporation, a quartz crystal is used. Now the crystal needs to be cleaned or changed periodically. So there are various steps to use the crystal monitor. First is switch on the crystal monitor. Second, depending on the material to be deposited, select the film number, enter the density of the material, acoustic impedance, tooling factor. Next, when evaporation begins, press the start button, set the thickness display to 0 and open the shutter. Now once the desired thickness is achieved, close the shutter mechanically and press the stop button. So students, let us now discuss about the electron beam or E-beam evaporation. E-beam evaporation is a physical vapor deposition process in which an intense beam of electron is generated from a filament and is guided via electric and magnetic fields to strike the source material and vaporize it within a vacuum environment as shown in this figure. It is an important deposition process as the user can evaporate materials that are very hard or impossible to process using standard thermal evaporation. Some of the examples of such materials are high temperature materials like gold and titanium, and also ceramics such as silicon dioxide and alumina. Generally, extreme end range of pressure is required for running e-beam evaporation process so as to allow the employment of a wide ion beam source for the film densification and other modification of the property at the same time. So for generating an electron beam, an electric current is applied to a filament in the presence of high electric field. Electrons in the filament escape and accelerate away due to this electric field. Then these electrons are guided by magnets to build a beam and then get directed towards the source material placed on a crucible. So the electron's beam energy, it is transferred to the material and thus the material starts evaporating. Many metals like aluminium, it melts first and then begin evaporating, while ceramic materials get sublimated. The vapors of the evaporated materials then travel out of the crucible and thus the substrate is coated. So in order to increase the crucible lifetime, it is put up in a water-cooled copper earth during evaporation. There are various advantages and disadvantages of e-beam evaporation. The advantages of e-beam evaporation are: first, e-beam evaporation source allows the deposition of the material in larger amounts. Also, higher deposition rate is achieved. Second, the e-beam source can be equipped with a carousel of multiple pockets for depositing multiple targets sequentially without breaking the vacuum. Lastly, we can get high purity deposited thin films. Now, e-beam has certain kind of disadvantages also. These are: the process is difficult to be controlled, incapable of performing the cleaning of the surface. It is difficult to improve the step coverage. Pulsed laser deposition technique. One of the PVD method, that is pulsed laser deposition (PLD method), has become increasingly popular in the past few years as it is easy to use and successful in deposition of materials with complex stoichiometry. PLD is one of the best technique to grow high quality functional oxides thin films. So the schematic of the PLD setup is shown in this figure. Here, a high power ultraviolet wavelength pulsed laser beam is directed in a vacuum chamber, roughly 10 to the power minus 6 torr, for target ablation. The ejected material forms a plasma plume which then extends away from the surface of the target and interacts with the chamber's atmosphere until it arrives at the surface of the substrate where it gets deposited as a thin film. So, a laser beam of sufficient energy is focused on a target. The target material goes into the vapor state directly without melting. The vaporized species in front of the target are seen as glowing plasma called as the plume. The plume interacts with the processing gases, generally the reactive gases available in the deposition chamber, and the ablated matter is condensed on the surface of the substrate as a thin film. So, if the laser beam is intense enough, it can ablate the hardest and most heat resistant material also. In PLD, there is a provision for heating the substrate to assist nucleation and allows the growth of crystal. The processing steps of PLD are as follows. First, the absorption of laser on the surface of the target. Second, laser ablation of the target and plasma debut. Third, dynamics of the plasma. Fourth, deposition of the ablated target material on the surface of the substrate. Lastly, nucleation and growth of the film on the surface of substrate. Thin film deposition parameters in the case of PLD. First is the laser parameter. It consists of laser fluence in joules per centimeter square, laser energy, and the ionization degree of the material to be ablated. Second is the surface temperature. Nucleation density generally gets decreased with increase in the temperature. Third, surface of the substrate. Roughness of the substrate surface. Any miscut can affect the growth of the film. Lastly, the background pressure. This is needed for ensuring stoichiometric transfer from the target material to the film. So, in PLD, there are three possible growth modes based on the above deposition parameters. First, step flow growth. Miscuts on the substrate lead to atomic steps on its surface. Thus, atoms lands on the surface of the substrate and gets diffused to a step edge before being nucleated. The growing surface is viewed as steps moving across the surface. Second is layer by layer growth. In this mode, islands nucleate on the surface of the substrate till a critical island density is attained. When more material is added, the islands keep growing till the islands coalesce into each other. Hence, the surface has a large density of cavities. When more material is added to the substrate surface, the atoms get diffused into such cavities to complete the layer. This process is repeated for depositing subsequent layers. Third, 3D growth. This growth is similar to layer by layer growth, apart from the fact that once an island is formed, nucleation of the additional island takes place on top of the first island. Thus, the surface gets roughened every time a material is imparted. There are various factors influencing the deposition rate. These are target material, energy of the pulsed laser, distance between the target and the substrate, background gas type, lastly, the chamber pressure. Now let us discuss the advantages of PLD. Capability for stoichiometric transport from the target material to the substrate surface. In other words, procreation of the exact chemical composition of the complex material in the deposited film. Reliability, high rate of deposition, use of laser as an external source of energy leads to highly clean process without filaments. Therefore, both inert and reactive gases can be used as the background gases while depositing film. Carousel for holding multiple targets enables the deposition of multi-layer films without the need of breaking the vacuum in while changing the material in between. The disadvantages of PLD are chances of non-uniform thickness and varied composition across the deposited film, as here the plasma plume formed during the laser ablation process is extremely forward directed. However, this problem can be tackled by rastering of the laser spot across the target material or by substrate rotation during the deposition. So the area of the deposited material is quite small, approximately 1 centimeter square, compared to that required for several industrial applications. Deposition of novel materials requires periodic empirical optimization of deposition parameters. Sputtering. Sputtering is another PVD technique to deposit thin film of a material onto a substrate. So it can be divided into 3 stages. Firstly, the gaseous plasma. A plasma is an ionized gas consisting of positive ions and free electrons and neutral. Basically, it's the fourth state of matter is created in the vacuum chamber, and then the ions are accelerated from this plasma into some target source, that is bombardment of high speed particles with the source material. This leads to the momentum transfer from the particles to the atoms at the surface, and this imparts sufficient energy to the surface atoms to escape away. Finally, these ejected atoms can then travel to a substrate, and thus the film gets deposited. So this figure shows the schematic of the sputtering setup. Now there are some considerations or several factors which needs to be considered for sputtering deposition. First, creation, control and directing of high-speed particle stream. Next, interaction of such particles with the material source surface and emission yield. Next, the deposition of ejected target atoms on the substrate. Lastly, quality of the deposited film. So in sputtering process, the target material and the substrate are placed in a vacuum chamber. Voltage is applied in between such that the target acts as the cathode and substrate as the anode. Ionization of gas, a chemically inert heavy gas, such as argon in general, results in the creation of plasma. This sputtering gas then bombards the target and sputters off its surface. Let us discuss the first type of sputtering, that is DC sputtering, and this figure shows the schematic of DC sputtering. DC sputtering uses a DC gaseous discharge. The power supply is a high voltage DC source. Ions bombards the target cathode source, while substrate and chamber walls may act as the anode. The main control is the energy range of the ions. Now, limitations of the DC sputtering are: first, high pressures required for attaining plasma can possibly degrade the quality of the film. Second, only little fraction of gas is changed to ions. Third, low deposition rates. Lastly, limited to the materials of resistivity less than 10 to the power 6 ohms. No insulators, as they require impossibly large voltage for sustaining plasma. AC plasmas. Since the effective resistance of dielectrics varies with the frequency of applied current, thus a capacitor coupled AC plasma sputtering system holds lower impedance and thus requires reasonable voltage for sustaining current through the target. At low frequencies, as both the electrons and ions reacts to the change in voltage polarity, crucially a DC plasma changing sides dominates. So above frequencies, that is approximately 1 megahertz, since the ions are heavier, only the lighter electrons they are able to follow the change in voltage. So the high mobility of electrons renders them to be more energetic and thus increases the density of the plasma. Self-biasing of the target. The target automatically tends to bias itself more negatively than the anode as a consequence of the difference in the mobility of ions and electrons. The reason is that high mobility of electrons enables them for a larger electron flow through the anode, while the less mobile ions provides a lower current to the cathode. Due to this asymmetry, a negative biased current is created through the plasma. Next type of sputtering is RF sputtering. So this figure shows a schematic of RF sputtering. In RF sputtering, there is a cathode, that is a target, and anode in series with a blocking capacitor C. The capacitor is included in an impedance matching network utilized for optimizing the power transfer from RF source, often constant as 13.56 MHz to the plasma discharge. The blocking capacitor C is used in the circuitry for developing necessary DC self-bias. The advantages of RF sputtering are: RF sputtering has an advantage over DC as building up of ions is prevented for electrically insulating targets by avoiding constant negative voltage on the cathode. Second, operating pressure can be low for sustaining plasma. Disadvantages are: deposition rates are lower and power supplies are expensive. So the next or the last type of sputtering is the magnetron sputtering, and this figure shows the schematic of magnetron sputtering. This is magnetically aided discharge. As we know, in DC and RF sputtering, electric field is perpendicular to the target surface. However, in the magnetron arrangement, a permanent magnet or electromagnet is added to the system for creating magnetic flux lines parallel to the target surface. This magnetic field concentrates and intensifies the plasma immediately above the target due to the trapping of electrons near the target surface. This leads to enhanced ion bombardment without the need of increasing operating pressure, as it degrades the film quality after a certain point and sputtering rate for both DC and RF. So it uses a matching network whose schematic is shown in this figure, which is used for RF plasma coupling. So students, let us summarize what we have learnt in this module. First, the fundamental physics of the physical vapor deposition process is discussed. Second, detailed study of various types of PVD methods and the difference in their growth processes are discussed, and these processes were discussed are thermal evaporation, E-beam evaporation, pulse laser deposition, sputtering. Advantages and disadvantages of all these methods were also discussed in detail. Thank you.